move it, move it. I like to move it, move it. I like to move it, move it. You like to move it.
Hello, and welcome back to I Like to Move It, the podcast where we explore the incredible logistics and engineering behind the things that power our world. We hope you all had a fantastic holiday season. Welcome back after the Christmas break. I'm your host, Mr. R, and as always, I'm joined by my fantastic co-host, Alice.
Hey everyone, it's great to be back. Today we're diving into a fascinating topic that's literally in your fizzy drinks and helps grow your food. We're talking about phosphoric acid production plants, where chemistry meets engineering to power global agriculture. From transforming raw minerals into fertilizers to the massive machinery and precision logistics behind the scenes, these plants keep our food supply and industries running. It's the hidden tech that moves the world.
Absolutely, Alice. And to guide us through the complex world of phosphoric acid production and the massive engineering behind it, we're thrilled to have a very special guest with us today, Francesco Onori, an expert in the field. Francesco, welcome again. Your enthusiasm and clarity always make these episodes a joy. Thanks for being here.
It's great to be back. Today we're diving into another fascinating journey through industrial engineering. And we're thrilled to welcome back Francesco, who's become a real friend of the show. Thanks for joining.
Thank you, Mr. R. Alice. It's a pleasure to be here. I love sharing what we do and helping people understand the complexity and beauty of industrial processes.
And we love having you. For those tuning in for the first time, Francesco is one of the founders of Cavart, an engineering company specializing in industrial plants. Francesco, can you tell us a bit more about Cavart?
Absolutely. Cavart was founded in 2006, building on the experience of my design studio. We've always focused on industrial engineering, from glass recycling facilities to fertilizer plants, phosphoric acid production, grinding systems, and dosing of solid raw materials. Basically, everything mechanical within an industrial plant. We collaborate with specialists like chemists to make sure everything runs smoothly.
Francesco, let's start with the basics. When we hear acid, it often sounds a bit scary. But you mentioned phosphoric acid is in some surprising places. Can you tell us a bit about what phosphoric acid is?
Of course. It might sound intimidating, but phosphoric acid is actually an acid that isn't particularly aggressive. In fact, when it's purified, you can even drink it. It's the acid you find in carbonated drinks, for example. That sensation you get when people say carbonated drinks can dissolve rust from bolts, that's thanks to the phosphoric acid in it. I believe it's specifically called orthophosphoric acid, though I'm not a chemist, so don't quote me on that exact name. Generally, it doesn't cause many problems and isn't very reactive. I've even seen it stored outdoors in open tanks.
That's amazing. Quite a contrast to what many of us might picture. So, if it's in carbonated drinks, it must be widely produced. How exactly is phosphoric acid made? And where do the raw materials come from?
Well, it's produced from phosphorus, and phosphorus is primarily found in phosphatic sands. These sands are predominantly located in deserts. The reason for this is quite interesting. Deserts are often alluvial deposits from seas that existed millions of years ago. Phosphorus was present in the cells of animals and living beings in those ancient seas. When the seas dried up, all these elements, shells, various animals, precipitated and formed these phosphatic sands. These sands are essentially phosphates, or as we might casually call them, phosphatic rocks, because they're a mix of various rocks containing phosphorus, along with silica, calcium, and carbonate. To use these phosphatic sands, both for agriculture and to produce phosphoric acid, they need to be attacked with sulfuric acid. Sulfuric acid, on the other hand, is a very aggressive acid. This means that upstream of any phosphoric acid production plant, you absolutely need a sulfuric acid production plant. The sulfuric acid then aggressively attacks these rocks, breaking down the phosphorus element, which is in the form of P2O5, and making it available.
So sulfuric acid is the key to unlocking the phosphorus. Once that reaction happens, what's the next step? How do you actually extract the phosphoric acid from this mixture?
After the sulfuric acid attacks the finely ground phosphatic sand, you get what we call a slurry, an amorphous mass, almost like a jam. This slurry is then fed onto special filters. We use something called a tilting pan filter, which is essentially a rotating carousel with many wedge-shaped sectors. As it rotates, these sectors are filled with this reacted paste. In a specific zone beneath, a vacuum is created, which sucks the liquid part through, leaving the solid part on top. As the carousel continues to spin and all the liquid is extracted, when it reaches the diametrically opposite side, these filters are tilted 180 degrees. This causes the solid part to precipitate and separate. Then the filter straightens up and gets refilled with the paste, making it a continuous process. And
That's a very clever mechanical solution for separation. And what about that solid part that's left behind? Is that just waste, or does it have another use?
the solid part that remains after the extraction is predominantly calcium sulfate, which is essentially gypsum. It's often humid and sticky. While it's a byproduct of the process, it's still a solid material that needs to be handled. We load this gypsum onto our machines and transport it to a final stockpile for definitive storage.
That leads us perfectly to what your company, Cavart, does in all of this. You're not producing the phosphoric acid itself, but you're integral to the operation. Can you elaborate on Cavart's specific role?
You're absolutely right, Alice. We're not the owners of the chemical process itself. Cavart is a company that provides ancillary service machines for these large industrial processes. Our core expertise lies in all the transport and connection systems between the various process machines. We focus on what we do best, building machines that serve other machines. For example, when the phosphatic sand arrives at the production site by truck, we transport it. It's unloaded into hoppers that we design. Below these hoppers, scraper chain extractors feed the material onto long conveyor belts, often around 300 to 400 meters in length. These belts then carry the material to the grinding plant. The sand arrives from the quarry in pieces ranging from 0 to 5 millimeters, but it needs to be reduced to a fine powder below 500 microns. While other companies make the grinding mills, we supply all the machines that transport the sand both before and after it's ground. Once it's finally ground, this sand is stored in silos, with each silo holding about 1,200 tons. We then extract it again, typically using augers, and transport it to the reactors where it mixes with sulfuric acid to form the slurry. And as I mentioned, we also handle the solid gypsum byproduct, transporting it to its final storage. For our large and long conveyors, we rely heavily on Rulmeca components like rollers and support stations. We choose Rulmeca because in such a demanding environment, it is absolutely essential to have components that can withstand these harsh conditions. And Rulmeca products do exactly that, ensuring an unparalleled continuity of operation.
It sounds like in this project is the circulatory system of these plants, ensuring everything flows smoothly. Given the need for phosphatic sands, where are these massive phosphoric acid plants typically built? Are they scattered globally, or are there specific regions?
These types of production facilities, like phosphoric acid plants, are most conveniently located where there are natural deposits of phosphatic sands. For instance, we're currently building a plant in Egypt because they have vast deposits. Other rich areas include Morocco and the entire Maghreb region. It makes logistical sense because it's easier and simpler to transport the finished liquid product, the phosphoric acid, than to transport vast quantities of sand. These are typically large industrial complexes, often spanning several hectares. While the core processing plant itself might not be enormous, perhaps 5,000 to 10,000 square meters, all the auxiliary areas before and after the process require significant space. They are usually built adjacent to other industrial facilities like fertilizer plants and are generally isolated from residential areas.
That makes perfect sense to minimize transportation costs and impact. Speaking of safety, you mentioned sulfuric acid is very aggressive. What kind of safety measures are paramount in these plants, especially concerning the different chemicals involved?
Safety is absolutely crucial in all industrial plants. While phosphoric acid itself isn't aggressive in its normal state and usually doesn't pose problems, the primary safety concerns revolve around sulfuric acid. Sulfuric acid is highly aggressive and has a strong affinity for water. It will aggressively capture any water molecule it finds. So, extreme caution is needed when handling it. Beyond that, other substances like ammonia also pose significant risks. When you combine an acid like phosphoric acid with a base like ammonia, you're dealing with risks of explosivity, so extreme care and attention are required. In many so-called Western countries, these types of plants have been largely delocalized to emerging nations. This is partly because those nations are investing in producing these commodities, but it's also sometimes speculated that it's due to less stringent oversight or attention to regulations in some of these regions, although safety standards are still present.
That's a sobering thought about the delocalization. You mentioned fertilizers earlier. How does phosphoric acid fit into the world of agriculture and plant nourishment?
Phosphoric acid plays a vital role in fertilizers. When we talk about phosphates in the context of agriculture, we're usually referring to phosphate-based fertilizers in solid form. There's a distinction. Single superphosphate. If you simply attack a phosphatic rock, which we casually call phosphate, with sulfuric acid, you make the P2O5 molecule available for plants. This produces single superphosphate. The conversion rate of the phosphatic rock is roughly 15 to 20%, resulting in a phosphorus richness of about 18%. triple superphosphate, TSP, to create a much richer and more potent fertilizer. Instead of attacking the phosphatic rock with sulfuric acid, it's attacked with phosphoric acid. Since phosphoric acid is already a processed product, it yields a much higher richness, reaching 43 to 44% phosphorus content. This enriched product is called triple superphosphate, or TSP. It's still a solid fertilizer, typically granulated or distributed as a powder directly onto fields. So, while phosphoric acid can be used in its liquid form for various applications, it's also a crucial component for producing highly effective solid fertilizers.
That's a great distinction. Can you give us some insight into the complexity of designing these transport systems, especially when dealing with such varied materials?
It's true. Nothing we do is off the shelf. Everything is custom designed. Transporting solid bulk materials might sound simple, but it's far from it. We need to know the material's characteristics intimately, how aggressive it is, how much it sticks together, how much wear and tear it causes. Each material requires a detailed study of its fundamental characteristics. For example, when you compare transporting phosphatic sand to, say, glass cullet from a recycling plant, they present different challenges. Glass is extremely abrasive and can wear down any surface it touches. Sand, typically 0 to 5 millimeters, is generally less aggressive. However, if sand gets wet, it becomes very sticky, leading to problems with it adhering to conveyor belts, requiring scraper systems to keep them clean. For very fine materials, we might not use traditional conveyor belts but rather augers. The limitation with augers is they can't cover long distances. In such cases, if a series of augers isn't feasible, we might consider chain conveyors, always evaluating the cost-benefit. So it's about making choices based on extensive experience. We learn a lot from our primary clients who provide us with all the necessary information, and we then apply our expertise as a service company. For instance, in our current project in Egypt, which is a doubling of a plant we did in 2017 to 18, we're incorporating improvements and eliminating past issues, even using special duplex steel in some machines for high resistance to chemical aggression.
Finally, these sound like colossal undertakings. What's the scale of investment and the typical project timeline for something like this?
These are indeed massive investments. An entire site can involve investments of around 400 million euros. Such projects require large companies with the trust of the client. The process often begins with feasibility studies and quotations to provide indicative costs to the client, which can take 3 or 4 years. After a couple of years of discussions, a contract is eventually signed. Once the contract is in place, the executive design phase begins. For us, this means designing our machines, but also many structures that will be built directly on site. We provide the detailed executive drawings, and the client constructs heavy, low-value components locally. For example, the carpentry for a 300-meter conveyor belt is made locally based on our designs. We then go on site to coordinate the assembly of these components. It's a long process, but it's how these crucial industrial complexes come to life.
Francesco, that has been incredibly insightful. From the very atoms in ancient seas to the massive machinery moving them, and the critical role your company plays, it's truly a journey of complex engineering. Thank you so much for sharing your expertise with us today.
My pleasure, Alice, Mr. R. Thank you for having me.
Well, that brings us to the end of today's episode. Let's take a quick look back at what we've explored together. With Francesco, we discovered how phosphoric acid is at the heart of some of the world's most essential industries. We learned how it's produced, how Cavart designs and builds the machinery that makes such large-scale operations possible, and how components like Rulmeca rollers ensure these plants can run continuously, even under extreme conditions. But most importantly, we've seen why phosphoric acid matters so much. It's not just another chemical, it's the backbone of global agriculture. Over 80% of it goes into fertilizers that help feed billions of people. It also finds its way into everyday life, from the tangy taste of soft drinks to the protection of metals, the making of detergents, pharmaceuticals, and even electronics. In short, without phosphoric acid plants, modern farming, global food security, and a big part of our industrial world would simply not be possible. So next time you see a conveyor belt carrying tons of raw material, or you sip a fizzy drink, remember, behind it all there are incredible engineering solutions, people like Francesco and his team, and a complex chain of innovation and reliability keeping the world moving. Thank you, Francesco, for once again sharing your passion and knowledge with us, and thank you all for tuning in.
We hope you've enjoyed learning about the alchemy and the incredible logistics behind this essential commodity. Join us next time for more deep dives into the unseen movements that shape our world. Until then,
have an amazing 2026 ahead. Take care and keep being awesome.
I like to move it. I like to move it.